Hi there and welcome back to Triplicate, and I was going to finish the last video on the Radical Synth, the Heresy, on the coupled mass stuff, but while I was supposed to be editing the video I was sort of carrying on and trying to work it out, and as you can see I ended up covering rather a lot of paper, but I have moved on and I thought I'd move straight on with this video because if I put it down and leave it now, by the time I pick it up again I'll have forgotten where on earth I am and what on earth all these equations are relevant to. So, moving on. Okay, so I tried to set up some way of calculating the frequencies that are output when we have multi-spring spring and mass systems where all the masses are not exactly the same. So here we have a system. So we're assuming one mass has a mass of 1 and an amplitude of 1, and the other mass has a mass of m and an amplitude of a. And we're also assuming that these masses will either be together or in antiphase, or, and we'll come to this, one of them can be stationary. Okay, so that means if you look at this mass, it sees this spring here and this spring here, and because that mass is, say, moving that there like that, always in phase or out of phase, it makes this spring seem like a spring that's connected to a fixed one end with a different K, with a different spring constant, an effective spring constant that I've called K1 and K2. So for the case of one mass where we fixed one end, the effective spring constant was 2 springs, 2K, because both springs were pulling the mass back towards its 0 point. In this case, obviously, because that's A1 and that's A, these two K's will be different. Now for the case where they're both moving together, if M is 1 and they're both moving together, that spring will effectively be naught. It won't ever be stretched or compressed. Okay, so these are resonance equations with our two virtual spring constants and our variable mass in. So we can write equations of motion down here, and for K1 and K2 from the force on both masses, and A the amplitude. So here we go. So we've got K1 and K2. So we can substitute back in down here, and we get here a quadratic equation for A. M, remember, is something we're specifying, and down here we go till we get the actual. So here is the quadratic function, and down there we substitute in that, and we get eventually to that. So we've got our value of A, and we can find K1, ohms squared, hence K from K1, and K1 from that equation. And here I've just tested, and it does give the correct results, which agree with my experiment. I just swept frequency through the two mass system for various masses, so I'm happy with that. So now we can quickly find the resonant frequencies given our mass, so we can just calculate for various m's where they are and see what pans out of that. Okay, so I've done some calculations in a spreadsheet solving that quadratic equation, and we have a graph here which shows F1, the lower frequency, which you can see comes up and actually starts to level off. F2, the upper frequency, that's with the bigger mass, which goes up roughly at an angle, and that's the ratio. And if we look here at the ratio, interestingly, if we highlight the 1.5 and look at the ratio is actually 2.00246. So that foxed me a little, really. I thought, oh, 1.5, that's a nice number, there must be some kind of a simple equation there. There isn't. It just happens that 1.5 gives very, very nearly the right answer, the ratio between the two frequencies being 2. However, so we can do it with two masses. We could keep fiddling the mass details in this spreadsheet until we got very, very nearly 2, but 2 isn't really what we want, so let's move on and try 3 masses. Okay, 3 masses. So here again, the first mass is 1, amplitude is 1, and here I've called that K0. Terrible writing. K1 for mass 1, so mass 0, mass 1, mass 2. K1 for mass 1, and its displacement is A1. K2 for mass 2, and its displacement is A2. So we can write force equations, and from those get our effective spring constants, K values. And here we go. Well, here's our frequency relationship between our K values, masses and frequencies, and we've got 3 force equations. Yeah, so here I took this ratio value and calculated those, but I decided that wasn't the way to go, so I ended up with substituting in these equations and getting these 2 equations. Okay, so can we solve these? They're just simultaneous equations. Can we solve them? No. Yeah, we're trying to solve them for, I put A0 in here, but that's actually 1, but can we solve them for A1 and A2? Unfortunately not easily, because we've got these 1 over terms, which means if we expanded them out we'd have squared terms, and we would be trying to solve simultaneous quadratic equations. Don't know whether that can be done, but I sort of shied away from trying that. Okay, so having concluded my easy way of doing this, wasn't that easy at all, I decided to go back to the conventional way of doing it and try and get my head around some mathematics, which I must have done at some point, but it was probably 40 odd years ago and I cannot remember a thing. So here we have 3 masses. So this is a guy called Michael Richmond, which I sort of kind of like his style, but if you Google coupled oscillators, you'll get quite a few of them, and they are all pretty much university lecturers, university texts, so don't expect easy sums. So yeah, we can write some matrix equations here, and you can see he's put m outside, but surely if the m's were different we could put m's in here and do our matrix sums. You see, they're not trivial for the same masses, and come out with our omega 1, omega 2, omega 3 here. So I sort of sat down and set out to try and learn matrix calculations, you know, try and familiarize myself with what's going on here. But whilst scanning down this, I discovered, so yeah, it goes through 4 masses and does a brief look at many oscillators, which he says he does in a later lecture, which I've only skimmed through, but he gives us this equation, which for identical masses gives the frequencies out for, which is n, which is the mode, and n, which is the number of oscillators. So you can see below he gives n equals 2, and you get those two, which we know n equals 3, that's big N, so that's n equals 1, 2 and 3, etc. However, he also says down here, which is true, if n, small n, is much smaller than large n, this equation approximates to this, so the harmonics are then linear. So I think we could run quite a few masses without loading down the processing, and that solves the problem of having to deal with all these weird frequencies and find out what they are. Now, I might go back to that, but for now we are going to look at this and use a large number of masses and see what we get. Okay, so we've tried it. So equal masses equals spring tensions, spring constants, and here we have 2 masses, 3 masses, 4 masses, 5 masses, 10 masses, 20 masses and 50 masses. So I've effectively plucked a set off with the mass y displacement at non-zero, half of them, then a fifth of them, then a tenth of them. So let's listen to that. Okay, and I think you can hear as we get especially to the higher numbers, it does sound more like a harmonic sound than a strange bell-like thing. So let's now try, because we get a lot of harmonics at the top, let's try. We'll take our 50. And we will keep, what, 10 harmonics-ish. From 200 Hertz is 2000 Hertz or so. So we will set up a filter. Okay, and have a look at the spectrum as well, shall we? Well, we'll play this. I think that sounds okay. So now we want to drive it. Remember using our, I suppose, bow model. So when the velocities match, it gives a kick to the input. But we need to think about this before we just do it, because we now have many masses we're driving rather than just one. Okay, so here we've got 20 masses. See how that fares. We could go up, could go down. We're driving mass number 5, and we're taking as our outputs the 10 and 0, the middle and one end. So we run that up, and what does that give us? That gives us this. Now we have a single tone, which is supposed to be 440 Hertz, concert A, and a rising tone. So that sounds like this. So it's working, and it does actually sound a bit recorder-like, so kinda happy. But if we look here and pull the spectral analysis where you can see it, it's kinda, well, it's kind of going at 860, so it's a bit flat. This big peak is what I guess it's taking as its frequency. So it's a bit flat, and it's concentrating on the first harmonic. Okay, so what I propose now to do, shall we move where we're bowing it? So we're only bowing one. We're only driving one of the masses. Now I thought we'd probably have to drive several at some kind of an average, but let's just drive one at the end and try driving the middle one and see what that does. Okay, so we're driving the middle, so let's see what this does. And you can see we've got certainly a bigger one here. Oh, there we go. So that's driving more the fundamental. Okay, so that is driving the fundamental rather than the first harmonic. And it probably is, sorry, it probably is a little flat. Let's have a look at this. Let's let you have a look at this. So, yep. See, the biggest peak is at 440. I'm starting to like this. So what will we do now? Let's put it right at one end, say 1. Okay, so we run it up. And it's outputted some text if we want to put it in a spreadsheet, which I don't think we need to at the minute. Right. Okay, let's see what that sounds like. Oh, so that's right at the end, bowing it right at the end. That doesn't seem to work brilliantly. Interesting though, interesting. So we can change the tone by varying the bow point or the drive point, and let us finally actually try driving several points. I don't know whether this is going to work. So we're going to drive 5 to 7. No, try 8, drive 3, no, 4 to 8. Oh, didn't mean to do that, come on. 4 to 8, this might not work. Okay, but here we go, let's give that a whirl. And load it in. Stop it. See what happens. Whoops. Try again. Oh, there we go, that's worked. Should we try that? Go. That has worked. Right, I need to think, what now? Okay, tell you what, let's try down at a few masses where if we just plucked it, it was very inharmonic and clangy. So I'm got 6 masses and we're driving mass number 2. So if we fire this up, and run it, there we go. Let's do that, there we go. So what have we got here? Let's have the spectral analysis back. It's a more useful thing to see. Oh, there we go. It's harmonic. You can hear it's harmonic. So we get a completely different situation when we drive it than when we just let it run freely. So let's delete that and let us try 3 masses. And we will drive mass 1, shall we? Let's see, let's try driving mass 1 and we will wait for it to compile. And run it. Let's see what we get. Alright, that looks nice. So, shall we play it? So again, harmonic, apart from just as it's coming in, we get these other inharmonic elements appearing. Interesting. But I am surprised to see it actually comes up with a harmonic when we drive it. Could have saved quite a lot of time and mathematics if I'd known that before. Hey ho. Okay, think I'm going to finish this one here because all this mathematics takes quite a lot of time, so I end up with a 20-minute video that's taken me a week to make. So I think we have enough to make a instrument, so I think it's best to put it back in the actual Heresy and see how it plays, see what happens. And I have to do something about the turntable, which I took one that worked was too heavy and made one that wasn't too heavy but didn't work properly, it was too sticky. So we might be on to the Mark III, or I might go back to the Mark I. I'll have to decide. So until the next one, which will be on something different because I've spent quite a long time wrestling with coupled mass equations. So until the next one, it's a goodbye from Triplicate. Oh, and I will see if I can calculate those coupled mass equations using the matrices and learn the matrices just for my own entertainment. Might make a video on it if it's interesting. But as it turns out, it's not really relevant because when we drive it, it seems to be force it into being harmonic anyway. Goodbye.